Welcome back to ECE 220. Couple of reminders. Today is Friday. Tomorrow your passport assignment is due, and your last sort of experimentation with homework assignment 0. That's when that's scheduled to be complete. So if you want to play around with mastering, do that today and tomorrow. And then the next few days, the official homework begins, homework number 1, and then every subsequent Tuesday thereafter is a homework assignment until we get into finals. We'll have 15 more, or 15 total homework assignments, and the first one is due on Tuesday the 3rd, which is the first day back from an extended weekend. We will not be meeting in class on Monday. Today what I want to do is continue in Chapter 2, and this really finishes Chapter 2. If you want something to do over the weekend, you need to now be doing Chapters 1 and 2. That's complete, and starting Chapter 3 next week. That's where we're at. Today we will begin with Kirchhoff, and we'll do a couple of laws. Kirchhoff's current law and Kirchhoff's voltage law, KCL and KVL. Again, for texting purposes, we have the 3 letters that we just need to keep track of. KCL and KVL. We'll work a couple of examples, and then we'll get through or attack one that involves dependent sources. The first 2 will have independent sources, but once we introduce a dependent source, that now says, oh, that particular source actually depends on some variable in our circuit, somewhere else other than where that source is appearing. This is somewhat of a reminder of your last your assignment that is due on Saturday. You need to provide me with a picture, and luckily Kirchhoff is now officially enrolled in the class. He's provided me his picture, and he was living in over 100 years ago, and he created these laws as a German physicist basically to go a little bit beyond Ohm's law. Ohm's law was concerned with one circuit element. Now we want to interconnect circuit elements. Right now we have independent sources, dependent sources, and resistors to interconnect. How can we systematically sort of approach the analysis of those problems? And that's what Kirchhoff provides. He provides us with some laws that are really based on conservation principles to analyze or help us in analyzing these circuits. And the first one is the current law, Kirchhoff's current law, KCL. And that is stated here in the red box, and that says that the algebraic sum of all of the currents at any node, and a node is just an interconnection between elements in your circuit, the algebraic sum of all the currents at any node in a circuit equals 0. And you might hear that stated several different ways, but they're equivalent ways of capturing that same idea. Here, the key is algebraic. We're distinguishing between the direction of the current at the node. That's what I mean by algebraic. If one is coming into the node and another one is going out of the node, we need to establish one of those as being in the opposite direction and giving it an opposite sign. Meaning, if we had 4 currents coming in and 2 currents going out, let's consider the entering ones to be positive, we would have 4 currents with positive signs and 2 with negative signs. That's the algebra, or the algebraic sum of the currents at any node. We could restate that KCL expression or concept by saying, let's just talk about all of the currents entering a node. Then if a current is not entering a node, we give it a minus sign and say, oh, it's entering with a minus sign. Here, the sum of all the currents entering a node equals 0. That's equivalent to the previous statement. Well, if we come into a node, we can also exit a node, and that's the next equivalent statement of KCL that you might hear. I might even say it here. I might say, let's sum the currents leaving a node. And now that says the sum of all the currents leaving a node equals 0. And this is something I might do at a particular node when we're doing Chapter 4 analysis. When we're doing node voltage analysis, I might say, oh, the sum of all of our currents leaving this node must equal 0. I'm just stating KCL, and that's what's happening at that particular node. And that's equivalent to the two previous statements. And finally, we could say, oh, well, let's just kind of keep these on two different sides of the equality sign. Let's put one group, which are entering, let's put those entering equations on one side of the equality sign, and let's put all the exiting currents on the other. And now we say the sum of the currents entering the node equals the sum of the currents leaving the node. And all of those are equivalent statements. And I might say that in any of these forms throughout the semester, and you might hear it or see it in written material or presented material. Somebody might say, oh, let's set the currents entering equal to the currents exiting. That's just KCL. Here is a node with a big black dot in the center. Those are now all connected wires. Sometimes you might see wires that overlap, but they don't intersect. So you need to make sure in a schematic or in a diagram, are these wires interconnected, or are they just passing by each other and they're insulated and they're not interconnected? Here, by the emphasis of that dot, I'm saying all of these wires are interconnected. And based on this interconnection structure, we have 6 different wires coming into the same node. We can apply these different strategies for expressing Kirchhoff's current law. The first one is the algebraic sum. What does that look like? Well, here we have to establish which one, or how we are assigning the signs, SIGN, to these currents. Let's just say that if a current is entering the node, we'll give it a plus sign. If it's exiting a load, we'll give it a minus sign. I sub A, how do we write that? Plus or minus I sub A. That's now entering, and we agreed for this explanation to keep that as a positive sign. We would now say, let me switch colors. For some reason I want to do blue. And I brought it back after it disappeared yesterday. I'm not sure how much you're following along with what I'm messing up while I'm presenting, but never mind. It's now back. I sub A. Plus, that's entering. What about I sub B? Same. That's now a plus I sub B. I sub C. That's not entering, it's exiting, so that has to have a different algebraic sign. That's now minus I sub C. I sub D. Plus I sub E. Minus, and I sub F, plus. The algebraic sum of the currents at a node equals 0. That's really just conservation of charge. Charge can't accumulate at a node. It has to kind of be going its different places and being conserved. KCL, that's one way of keeping track of those currents. Obviously, we would maybe have to express those. Right now, how many do we have? We have 6 variables. If we just had those 6 variables, we would need more equations in order to solve for those. And that's what we're trying to do then in this class, is figure out, oh, if I have this relationship, how do I use that to analyze the circuit? So we'll have to combine some of these different strategies that we have in our toolbox of techniques that we'll apply this semester. And this is one of them, KCL. What if we did it another way? What if we, let's say, what if we summed the currents in to the node? The algebra, or the sum of all the currents in equals 0. That's really just what we did. If it's not coming in, we have to give it a minus sign. It hasn't gone anywhere. We need to keep track of it. Even though it says sum of the currents in equals 0, well, if one is directed out, we just give it a negative sign and say, oh, it's coming in with a minus sign. We can't erase or forget or neglect currents that are directed out. We just give them a minus sign when we're using this formulation of KCL. In this particular case, all of the currents going in, well, we have I sub A, I sub B, minus I sub C. That's minus I sub C coming in. I sub D, minus I sub E, I sub F. Is that clear? So we're really just rewriting the last expression. But we're really trying to justify or convince ourselves that those different wordings of KCL are equivalent or capture the same information. What if I now said, what if I wanted to just think of these currents as exiting the node or going out of the node, and I wanted to write a KCL equation? I sub A, I need to keep track of minus I sub A if it's leaving the node. Or I need to write I sub A as minus I sub A to keep track of it. Or now I have minus I sub A, minus I sub B. I sub C is actually going out. I sub D minus I sub D is going out. I sub E is going out. Minus I sub F is going out. And this is why when students ask me if they're in high school, they say, what do I need to, how do I prepare for electrical and computer engineering? I said, really know your algebra. That's one of the things. And now these two equations, are they the same? Yes. You can do what? You can always multiply an equation by 1, and you can always add 0. Multiplying by 1 is essentially multiplying the top equation by minus 1 on both sides, and now you get the bottom equation that we see. So these are algebraically equivalent equations. Lastly, what if we wrote it this way? I want to sum the currents in and set those equal to the sum of the currents out. So do you see how we're sort of playing with words? And sometimes the syntax can get confusing. But here we're saying, let's just keep track of these currents and not be thinking about negating anything if we want it to be coming in. Let's just look at the diagram and say, how have I sketched or how have I labeled these currents? And if I've labeled some of them to be in that node and some to be out of that node, I just put the ins on the left and the outs on the right and set them equal to each other. In this particular diagram, we had 4 coming in, I sub A, I sub B, I sub D, and I sub F, I believe. Correct me if I'm wrong in my memory. And those are equal to the currents going out, which are I sub C and I sub E. Not changing the signs of anything, because now I'm keeping track of the signs or the directions by which side of the equality sign I'm putting them on. And now you could relate the extreme equations, the equation on the top of the screen and the equation on the bottom of the screen, by algebra. You could add I sub C and I sub E to both sides of the top equation, and you'll end up with the bottom equation. Algebra. Questions on KCL. Now, to test yourself, you should look at example 6 in chapter 2 to see if you're understanding KCL. KVL, the red box. They still have red boxes? Can we get a movie out of this box? Is that red box? Is that the right? Yeah, movies. Yeah. Okay. Is it still $1? Is it? Okay. Well, the movie is from what, 1980 or something? Well, then you'd have to pay $5 probably, because it's, never mind. So the red box here is the algebraic sum of all of the voltages around any closed path in a circuit equals 0. Now whenever you see KVL, you'll be thinking red box, and you'll be going, oh, I need to make sure I watch that movie. Is Kirchhoff in a movie? Maybe. You can watch that over the long weekend. That would be a fun movie, wouldn't it? Luckily, I'm not being captured visually on this recorded version. It's just the screen that's being captured. That's why you have to come to class, to see my visual interpretation of what I'm saying. All right? The algebraic sum of all the voltages around any closed path, and those closed paths can include air gaps, and we'll talk a little bit about air gaps later in the semester. So it doesn't necessarily have to be wires and elements forming that closed path. You could actually be, your closed path could be around an air gap. Hopefully that will make sense when we get there. Restating KVL. Well, now it involves drops, rises. That can get confusing, especially if I just start talking about it without showing any examples. So I'm not going to do that. I'm not going to restate KVL, but somebody might say, oh, we'll just sum up the rises of voltage, or just sum up the drops. That'll make more sense as we go through some examples. Let's look at some examples. Here's a schematic with 4 resistors, really just 4 elements. We're just concerned about their voltages. The voltages associated with those 4 elements, and this is in a closed box, or a closed interconnected configuration or wiring. And we have 4 voltages that are across those elements. Currents are through variables. Voltages are across. We'd have 2 probes in the lab and we would connect one probe to one end of the element and another probe to the other. We're measuring the voltage across. It's the potential. It's that energy per coulomb. That's the voltage. Let's now look at writing KVL based on this dashed line. That's the closed path that I'm now considering. And it's not even closed, it's dashed. But that dashed line is trying to represent the closed path that I want to sum these voltages with respect to, and I'm labeling it with a 1. This is KVL around path 1 is a way to maybe state that. And in symbols, I might say KVL, little clockwise dashed circle with a 1 in it. KVL around loop number 1, or mesh number 1, or path number 1. I might say it all of the above different ways. Meaning, this path means that you start at a node and end at that same node. That's a closed path. That's the closed part of it. We're starting here and we're finishing at that same location. And for me, I think it's just once you've labeled the circuit, just stick with the labels and write down the sign of that voltage's polarity that you encounter first in your progression around this closed path. Meaning, before I even write down V sub 1, what have I encountered? What sign have I encountered? A negative. So I would just say minus V1. I wouldn't say, oh, there's a rise, but it is a voltage rise from bottom to top through that element. But I'm just going to say, keep track of the signs that I encounter first before I go into that element or through that element. And that's how I'm going to then write down my equation. So I will say minus V1 plus V2 plus V3 minus V4, and then I'm back to where I started. Is that clear? I'm going to say minus V1 plus V2 plus V3 minus V4 is equal to 0. And if you wanted to think about it in terms of rises and drops, you might say, let's add the drops. The drops have positive signs. We're dropping. We're coming down the steps with V2. We're coming down the steps with V3. We're going up with V1, so that's a negative drop. And V4 is a negative drop. So this, if somebody wanted to talk about drops, you could say this is adding voltage drops. Or now I'm sort of restating KVL in equations. What if I said the drops equal the rises? What voltages drop as I move around in this clockwise progression around path 1? Which of these labels indicate a drop relative to the path that I'm traversing? What labels correspond to voltage drops? V2 and V3. Is that clear? So I fall down as I go through V2 and V3. Those are drops. So I would say V2 plus V3. And I'm setting those equal to the voltage rises as I move around that path that I've labeled path number 1. And where do I experience a voltage rise? I'm going up with V1, I'm going up with V4. Those are my voltage rises. So I would say V1 plus V4. So there's a second way of writing that. And do you see that those two formulations or equations are the same algebraically? You simply have to add V1 plus V4 to both sides of the first equation, and you end up with the second equation. So however you want to think about it, or if you see it written by someone else and you go, I haven't a clue how they ended up with that, but oh, I can manipulate with some algebra and I can get exactly what I had. So we must be getting the same thing. That's what you'll want to be doing if you're talking to someone else in the class or someone else in general, and they say, here's the equation that relates the voltages in this circuit. You go, wow, I don't quite see how that came about. But then you write your own and you do some algebra and you go, okay, now, yeah, we're on the same page. What if we had a variation on this? Suppose now that I said, oh, let's modify this and put an independent source between the corners, two particular corners in that circuit. And now what I want to do is write a KVL around path 2. Starting in the same corner, but now I'm going to sort of go immediately to go, or what's that in Monopoly? Do not pass go immediately. Why am I forgetting Monopoly? But anyway, we're going back to that beginning square in the lower left from the upper right-hand square. Funny things happen when you get in front of people sometimes. Your brain just goes off. So you guys have to help me occasionally. But now let's write KVL around path 2 in red. And if we follow the strategy that I suggested, let's just keep track of the signs that we encounter that we've put on there. And these labels, does it matter how we've labeled these? Based on a previous lecture? It doesn't really matter as long as we stick with the labels. Okay? It doesn't matter how we have assigned these labels. It does matter how we use them once they are assigned. In this case, what's my equation going to be around loop 2 or path 2? Does everybody see it? Minus V1 plus V2 plus V sub 5 equals 0. Minus V1 plus V2 plus V sub 5 is equal to 0. Or if you wanted to write it in terms of rises and drops, the rises equal the drops. What's rising? Do we have any rising voltages in loop 2? V1 rises. What drops? V2 and V5. We could have written that second equation, KVL, in terms of rises and drops and said V1 is equal to V2 plus V5, and that's exactly what we wrote before via algebra. One more KVL. See how many KVLs you could write just in this particular circuit? Suppose we now said, let's write around that one. Like I said, you have to pay attention. That's now mesh 3. Pardon? Could I pick a different starting point? Oh, of course I can pick a different starting point. Good question, though. So where do you want me to start? Now it's going to be challenging to erase that. But I'll honor the request. Where do you want me to begin? I didn't even hear what you asked. I apologize. Do you want to start in the top corner, the right lower corner, or the we were always starting in the left lower, right? You want to get away from that. Is that what I'm hearing? Typically, you want to write, when we're doing chapter 4, mesh analysis, you'll want all of your paths to be going in the same direction, clockwise, clockwise, clockwise. You probably don't want to be writing clockwise and counterclockwise. Then our sort of strategy, sometimes you'll go, well, I thought it was always this current minus that current. Well, what have you done? Now you've got one path counterclockwise and one clockwise. You've messed up the whole beginning or foundation of how we write these equations. But suppose that we continue clockwise, but now we start here. Is that variation enough? Now I'm starting in the upper right and progressing. How would I write my equation now? It would be plus V3 minus V4 minus V5 equals 0. And you would get exactly the same variables with the same signs if you started somewhere else. And you might just convince yourself of that. But here, what do we have? We have V3 minus V4 minus V5 is equal to 0. And if we wanted to, we could solve that for V sub 5 if somebody wanted that, and that would give us V3 minus V4. And suppose we said, well, let's just eliminate V5 from these last two equations that we've written. So let's take this equation, V1, which is V2 plus V5, and let's get rid of V5. And what have we ended up with? Well, if we add V4 to both sides, is that consistent with one of our other KVL equations that we wrote? The first one? The drops equal the rises, or the rises equal the drops. So we do have consistency. If you're starting to chase your tail, you better kind of be able to get your tail at the end, if you're chasing it. All right, let's do some problems. Let's apply KCL. Suppose now we have the following. Suppose I tell you that this is a current source that's 5 amps. This resistor is 1 ohm, and this resistor is 4 ohms. Now we have an interconnected, we don't just have isolated two-terminal elements that we're trying to apply Ohm's law to. Now we're trying to solve for voltages and currents. Maybe we're interested in power associated with this circuit. We want some strategies to accompany Ohm's law. Now in doing that, how might you label this circuit if you just said, well, I need currents and voltages in order to find powers. How would you label this diagram besides what you're given? This might be all you're given on an exam. And now you're asked, well, you might be asked to find, maybe you'll be asked to find V sub 2 or something. Or you might be asked, now I'm doing what I just asked you to do. How do we label this? You could say here's I1, or here's I2, or here's V1. Do you see how you kind of have to be neat, a little bit neat in your writing and keeping track of all of this? I could ask you to find any of those variables on an exam. But in looking at this, do you see anything that might be in common or might be able to help you simplify your thought process or the analysis? Do you see anything that's the same or shared in this collection of interconnected two-terminal elements? V1 is the same as V sub 2, is it not? Those have the same two nodes. Here, what you have to start getting comfortable with is the fact that these nodes can be big or you can shrink them down. You can virtually play with these wires. You can move these wires around as much as you want, or you can compress them. So that now, do you see we really have two nodes in this circuit, and the two resistors actually share the same nodes? They have the same voltage dropped across them. In this particular circuit, we can then see that in common we have V1 equal to V2. If this is supposed to be an example of KCL, do you see a node where we could apply KCL? I've now indicated two, so now all you had to have was a coin to answer that question, right? A or B, heads or tails. And either one we could use. We could use the top node or the bottom node, and they could be correct. Typically, well, the way we've sketched circuits, a lot of times we say, let's work with the top node. Let's apply KCL. I'm just going to call this node A. KCL at A. Have a lot of A's and ats. What does that look like? What's KCL at A? We could say currents in equal currents out. And if we simply write down, you're kind of stuck, you just say, well, I know 5 must be equal to I1 plus I2. Do you see where that came from? That's the sum of the currents in, that's 5, equal the sum of the currents out, that's I1 plus I2. That's KCL at A. And you could have said, oh, I just want to sum the currents out. Well, then you have minus 5 plus I1 plus I2 equals 0. And you'll get the same thing. But we can write I1 and I2 using Ohm's law. And we now know that V1 and V2 are the same. Let's just write them always as V1. And now we have one equation and one unknown. We were given R1 and R2. Now we have 5 is equal to V1 over 1 plus V1 over 4. Is that what I had assigned? Algebra. Now we can solve for the one unknown, and once we know that one unknown, we can solve for I1 and I2. We could clean this up. We could clear the fractions by multiplying everything by 4, and we now have 20 is equal to 4v1 plus v1, or 5v1. Or what's v1? V1 is now 4 volts. We can now use that to solve for I1 and I2 and now we know that I1 is 4 and I2 is 1. And does that make sense with this circuit? We have 5 amps coming in. We better have that many amps coming out. And they've now been divided among those resistors. We have R1 passing 4 amps. R1 is less than R2, and R2 is impeding more. It's resisting more, and it only has 1 amp. That's dividing the current among those two resistors, and we'll learn the current divider strategy later, but that's coming soon to a red box near you, right? It's Friday, okay? That was pretty good, actually. Okay, so coming soon is current divider. Let's work a KVL example. Suppose this one now is a voltage. R1 is equal to 2, and R sub 2 is equal to 3. I want you to find V sub 2. And this is our proverbial quiz. I'm not collecting it, but it's to help you get ready for the exams. Find V sub 2. And I'm giving you a hint. I said it's an example for KVL. Bless you. So now how do you apply KVL to find V sub 2? And now you can talk if you want. On an exam, I will not allow talking. Okay? You'll have to do your own work on an exam. But here, if you're struggling or need to nudge somebody or get some help, that's fine. Did you come up with an answer? Is V2 6 volts? What's in common here? If you labeled this, you would have V1 I1 through R1 and V2 I2 on R2. But do you see that the current's the same through both R1 and R2? And if you did that, let's just say that we had I1 there. Now a KVL equation around that path is minus 10 plus 2I1 plus 3I1 is equal to 0. That will give you I1, and you can now solve for V2 from that. I'll let you do that, or I might fill this in. Whoa, there was quite a bit of space, so maybe I can fill that in after class. But let's move on to another circuit that's a little bit more challenging. Let's say here's a 10 amp, and here is a 2 ohm resistor. Here's V sub x, here's a 5 ohm, and here's a dependent source of 11 V sub x, and now maybe somebody on the exam says you're supposed to find I sub 0. Find I sub 0 in that circuit. And now you're going, oh man. But just take a deep breath, think about it, and start looking and saying, okay, we have a dependent source. What are some equations that I can start to write that might help me obtain the information I need, which eventually is to find I sub 0? You could say, well, if I could find the current through V sub that second resistor, I would be able to solve using KCL and solve for I sub 0. What if I wrote a KCL equation at that particular node, at node A? Can we do that? Let's just write some equations down. Now we have KCL at A. 10 is coming in. What's vertically going down through that 2 ohm resistor in terms of some of the variable labels on our circuit? Ohm's law will give us the current down through that vertical resistor, will it not? That's V sub x divided by 2. And we already have labeled the current going out horizontally to the right. So there's one equation. That's now, unfortunately, has 2 unknowns, so we can't just immediately solve for either one of those. But we can find another equation that involves or contains those 2 unknowns. If we just look at that rightmost mesh, that rightmost pane in our window that has 2 panes, we'll call these meshes. The rightmost mesh, we could write a KVL equation around that. Let's now write KVL around 1. And what will that give us? Well, we'll just say minus V sub x plus, let's now use Ohm's law, from left to right through that 5 ohm, that's going to be 5 I sub 0 plus 11 V sub x equals 0. Minus V sub x plus the drop across that resistor, 5 I sub 0 plus 11 V sub x is equal to 0. There's a second equation and two unknowns, the same two unknowns. Now we can solve for either of those, and one of those is I sub 0. We're saying that this is coming from Ohm's law, which is now this, let's say, V sub 5 there. V sub 5 we just replaced with 5 I sub 0. If we simply did KVL in terms of V sub 5, it would be minus V sub x plus V sub 5 plus 11 V sub x. Now see if you can do the last two examples. Here's one that has what? Two equations and two unknowns, and you can solve for one or both of those and figure out what I sub 0 is. And if you needed to, you could solve for, solve for all of the powers and check your work. We'll pick up there after the long weekend on Tuesday.